Hello, I'm Yuan, a PhD student at University of Oxford. Today I'm going to present our resource paper, Machine Learning Friendly Biomedical Datasets for Equivalence and Subsumption Ontology Matching. The purpose of this dataset is clearly shown in the title, and the dataset will contribute to this year's Ontology Alignment Evaluation Initiative check, which I will talk about later. In the beginning, I would like to introduce the ontology matching or alignment task briefly by giving you an example. As shown in the figure, there are some subsumption axioms from two biomedical ontologies, FMA and SNOMED. And on the right-hand side, it's a tree graph visualizations of these subsumption axioms. So for example, the curly arrows here corresponds to this subsumption axiom, stating that the cranial nerve class is a subclass of neural tree organ class in FMA. And for the cross-ontology relationship, we have an example here, which says that the vestibulocochlear nerve structure class in SNOMED is a subclass of the cranial nerve class in FMA. And we can also have equivalent relationship here as an example, stating that the cranial nerve structure class in SNOMED is equivalent to the cranial nerve class in FMA. So through these equivalence and subsumption mappings, we aim to achieve knowledge and data integrations, or we can conduct quality assurance by, say, detecting the errors of each input ontologies. Ontology matching is challenging for both system design and dataset creation. On the system side, challenges can be variety of naming scheme brought by synonyms of class names or different naming styles of ontology designers. Second, we have ambiguity, where sometimes classes with similar names are not equivalent because they have different contexts within their ontologies. And third, there is scalability issue because naive traversal of OM takes quadratic time. So we need to design some sort of candidate selection algorithm to reduce the time complexity. Lastly, we have inconsistency issue because merging ontologies often lead to logical conflicts. Such conflicts can come from faulty mappings that need to be repaired or removed, but can also come from fundamental errors of ontologies or even a clash between new and old concepts. On the dataset side, there are several limitations for the existing ones. First, some of them lack high-quality gold standard mappings curated by human experts. As a result, the evaluation is less convincing and will be biased. And second, the traditional evaluation metrics are limited to certain use cases. So sometimes there are other kinds of systems, especially the machine learning-based ones, will use a different evaluation metrics. So we need a unified evaluation framework suitable for all kinds of systems. And third, current checks are often limited to equivalence matching without considering subsumption matching, which is also very important for ontologies. And lastly, current checks lack support for machine learning based systems because there's no data splitting and no intermediate comparisons for machine learning development. Let's bear in mind the aforementioned limitations of current OM datasets. Now I would like to introduce the workflow of how we create BioML datasets. First, we choose reliable ontology sources, in our case, UMLS and Mondo. They have human expert curation to generate high-quality equivalence reference mappings. And to generate scalable ontology pairs, we apply pre-processing and pruning to obtain sub-ontologies of specific categories. categories for UMLS refers to the semantic type, and for Mondo, the only category is disease because that's what the company focuses on. Note that the relevant hierarchies of the remaining classes in the sub-ontologies are preserved so that the ontology structure is not broken. So with the equivalence reference mappings, we can infer subsumption reference mapping. And note that we only select direct subsumers because they are the most challenging and they are related to the application of concept insertion. So when we want to place a new concept into an ontology, we need to find the most relevant or the direct parent. So there's also an optional class deletion algorithm, which is to subtouch any equivalence mapping that is used to create subsumption mappings. As such, systems cannot use equivalence mappings as an intermediate to infer subsumption mapping. They have to do it directly, so overall the task will be more challenging. With these two sets of reference mappings, we apply data splitting to support machine learning systems. And there are two kinds of evaluation, global matching and local ranking, which I will explain in the next few slides. And for the local ranking in particular, there's also an algorithm for generating selective negative candidates. This slide is just a wordy version of what I have described in the previous slide. So first of all, you can see that we generate reference mappings from two resources with industrial collaboration with Mondo and cloud sourcing from UMLS. And we apply ontology pruning for scalable pairs, and we incorporate not just equivalence mappings. Let's now go through the details of our evaluation framework, which contains global matching and local ranking. Global matching uses traditional precision recall and F1 metrics to evaluate the overall performance. However, high recall systems could be penalized on incomplete reference mappings because the number of false negatives will be increased. And local ranking uses ranking metrics such as hits at K and MRR to evaluate OM systems on distinguishing the correct mapping from a set of selective negative candidates. So our negative candidate generation algorithm in the paper basically introduces text level and graph level ambiguity to enhance the candidates. And second, local ranking evaluation is still informative on incomplete reference mappings. So we can see at least partial performance without penalizing high recall systems. And lastly, local ranking is a more efficient way for comparing or developing machine learning based systems. To provide a unified and fair workaround for comparing both machine learning based and non-machine learning based systems, we apply data splitting. So first, we have a holdout validation set for tuning hyperparameters of machine learning systems or adjusting configurations for non-machine learning systems, and a testing set for final evaluation. And third, there's an optional training set. Here we have two settings. The unsupervised settings does not have a training set, and the semi-supervised settings has 20% of the reference mappings as the training set. This is to mimic the case when a small portion of mappings can be provided by human experts. As a result, we generate 5 ontology pairs. 2 of them come from Mondo, and 3 of them come from UMLS. The category of each pair is shown in the middle column, and followed by the number of classes in each input ontology, and then the number of reference mappings for equivalence matching. The next table is for subsumption matching, where you may notice that there's a difference between the number of classes in the target ontologies because we apply class deletion algorithm to the target ontologies for a more challenging subsumption matching task. and the number of the subsumption mappings are shown in the last column. To promote better usage of our dataset, we established a new track in the OAEI. Here is an example of a result table for the NCIT to DOIT pair under the unsupervised setting. Results are tentative because by the time of this recording, it is possible to have more participating systems. So systems are allowed to freely choose different evaluation settings, equivalence matching, subsumption matching, or both, global matching or local ranking, or both, unsupervised or semi-supervised, or both. So this year we have 3 machine learning-based systems, BotMap, AMD, and Mercadillo, and the rest are rule-based systems. Mercadillo does not participate in the unsupervised setting but participates in the semi-supervised setting here, so you can see the results columns. And from just this table, you can see that the machine learning based system generally perform better than the rule based. The next is an example for the subsumption matching result between the SNOMED and FMA ontologies with category Birdie. So this year only 3 embedding based approaches participate in this track, and you can see that only local ranking evaluation is applied because the subsumption mappings are inherently incomplete. Some brief discussion of the result. First, system performances are not consistent across all on tasks. That means the first system is not always the first. And second, systems with high F1 scores do not necessarily have high ranking scores. And third, subsumption matching is more challenging, as you can see from the lower scores compared to equivalence matching. For more detailed results, you can refer to our OAEI report, which will come out later. For future work, we would like to improve the ontology pruning process by considering logical modules in order to preserve more context for the pruned concept. And second, we would like to construct more ontology matching pairs and consider anonymizing the testing set from the participants for more convincing results. And third, we would like to establish a collaboration loop between OM systems and human curators. This is to feed back high-quality system outputs, for example, consensus of multiple top-ranked systems, to the human curators, and ask them to refine the gold standard so that we can use the refined gold standard to evaluate our system again. And lastly, we would like to consider beyond matching just the named classes but also complex classes involving restrictions. So this is the ending slide. Thanks for all your attention.